Good afternoon, everyone. Thank you all for coming. So we are pleased to welcome Delincia to the stage today. And who will be our chairperson, Siddhant?
Hi, everyone. This is the first time I'm chairing a Zoom meeting. So Delincia has been with a part-time master's student from last year, June. She's currently employed by Ilovo, and her master's is focused on the application of industrial symbiosis, especially in the sugarcane industry. And she is the algorithm that she is applying for the case of industrial symbiosis is the stable matching problem. The stable marriage problem. So without further ado, I'll hand you over to Delincia.
Sounds like you were ready just in case you were asked this.
I figured it'd probably be me.
Sorry, Delincia.
Yeah, thanks, Sid. Good bio. Okay, let me just, can you give me access to share the screen, sir? Okay, can you see the full screen view? Okay, perfect. So as it said, I'm Delincia. I'm a part-time master's student. I work for Ilovo as a chemical engineer. And my topic is in the industrial symbiosis field, as many of you guys are. And I'm working on identification of chemical groups of waste, feed and waste streams for potential matching in the context of industrial symbiosis. So for this seminar series, I'm looking at a small piece of it, which is the introduction to the stable marriage problem specifically. So I won't go into detail about industrial symbiosis. I think we all know quite a lot about it, but just to touch base that in the recent years, we've seen quite a devastating impact of climate change all around us. And I think in the last year, we've seen it quite a bit as well. And there's really been quite a shift towards greener growth initiatives. And there's more focus around research surrounding this. And I think that's where our research becomes quite important. So industrial symbiosis is really the framework to allow companies to match their feed and waste streams in the most optimal way possible. And it's really about using the feed and waste streams in the most efficient way. And it comes down to one man's trash is really another man's treasure, and using that in the best way that we can. So the key part of any industrial symbiosis relationship is really identifying the trends and matching streams to identify possible relationships that could exist. So you've got this network of companies and you really just want to create the matches between them. However, the problem comes in is that as the number of companies increase, the data that you have to handle kind of grows exponentially. And then it becomes almost impossible for a human task force to handle this and to get accurate data out of it. So that's where our statistical and mathematical models will help combat this problem. Modern opportunities exist to create these matches of groupings of data. So where my research comes in, I am looking at creating the functional group matches between feed and waste streams. So as a start, I'll look at just a single product between a group of supply and demand companies. So you've got all your supply companies that are producing these products and they need to go to a specific demand company. So trying to create the matches between those two and then extending it to multiple products and then creating the network as you see over there. So you look at all feed and waste streams of all the companies and see where you can match them together. And then obviously you can break them down into functional groups and different chemical constituents and get quite fancy with that. And then the next step is once you've got your matches, you obviously want to create more efficient matches. So is it the best possible network or can we improve on it? So just to touch on matching algorithms. So matching algorithms, sorry, let me minimize it. Are algorithms that are used to solve graph matching problems in graph theory. And matching problems arise in the context of bipartite graphs. So a matching problem arises when a set of edges must be drawn that do not really share any vertices. And a bipartite graph is a graph whose vertices can be divided into two disjointed sets. So that's U and V, the other way around. So both sets do not have to be the same size, and every edge connects a vertex in V to a vertex in U. And some matches are obviously a lot more desirable than others, and this can be represented as a weighting. So your weighting can be represented in any form. So why are some matches more desirable than others? And you can look at transportation, such as distance, or maybe quality, or you can have a set of maybe criteria that you're following, maybe an ISO standard or a SHRC standard, those kind of things. And obviously you want the best matching to minimize this weight, whatever you choose it is. So there are some known matching algorithms that do exist, which I'll work my way through the course of my study. So currently I'm working on the stable marriage problem, which is what we'll focus on in this seminar series. And you'll see it's quite a simple, intuitive algorithm, and it does give you quite good answers, and it's easily adaptable into other forms. You then have the simplex algorithm, which gets adapted into the transportation algorithm, and research around this shows that it's more closely related to the problem we have at hand. And then the Ford-Fulkerson's another example, and Edmonds Carr. So today we'll look at the stable marriage problem. So just looking at marriage problems matching problems in general, they're all around us. And if we look close enough, you can see them in almost everyday life. So in the IT industry, matching algorithms are quite big in matching servers and clients. In the industrial network flows, so matching, this is where we are working in, matching companies, sources, and sinks. Online dating sites, not sure if anyone has some experience with that. Placement of medical residencies. So I'm sure we've all got friends in the medical field that wait at the end of their schooling careers as to where they're going to get placed across the country. Call center agents, incoming callers, and then matching roommates at a boarding school or university or as such. So in varying degrees across the world, matching algorithms have been used with machine learning and AI methods as well. So coming back to our stable marriage problem. So the real problem is you're given a certain number. So we'll work with men and women because that's how the stable marriage problem was developed. And it's quite easy and intuitively to explain it in this way. But at the back of your mind, just so think of the men as being the supply companies and the women as being the demand companies. So we'll go through it explaining the men and women problem, and then we can see how it fits into our context. So you've got a set number of women and a set number of men, and you're trying to find the suitable matching between these two. And if you look at this can be represented in a bipartite graph. So this just shows all the possible matchings that do exist, and you're just trying to create a pair between them. So just some background, the stable marriage problem was developed by David Gale and Lloyd Shapley in 1962. So quite a long time ago, and they proved that for any equal number of men and women, it's always possible to solve the stable marriage problem and to make all marriages stable. So I'll describe what that means just now. And it's always solved in O(n) squared time. And however, it should be noted that in the 1950s, this type of algorithm was already around in a program called the National Resident Matching Program. So matching your medical students to the hospitals. So it just probably wasn't documented as well. And then David Gale and Lloyd Shapley extended it and made it a bit more popular. And then depending on how it's used, you can either find a solution that's optimal for one participant or the other. So either optimal for the male group or optimal for the female group. So that's in the very basic form of the stable marriage problem. So what do you need as input? So you need equal number of two types of participants. So in men or in women, in medical students or in internships, or in supply companies and in demand companies. And then you need a preference list of each participant. So each participant needs to rank the other group of participants from highest to lowest. And then the edges represent all possible matchings. A perfect matching means each man gets exactly one woman and each woman gets exactly one man. So there's only one of each participant in a matching. So there's no polygamy in this situation. And then a matching is stable, as I mentioned before, is when there does not exist any match which both prefer each other to their current partner under matching. So a stable marriage, if you follow the David and Gail algorithm, it will always come out stable. And so, for example, a matching is unstable if there's a pair, example, let's say Raimo and Anne, who like each other more than their current match that they are in. So that means that they can dump their current match and make a pair together. So you don't want that. You want the most stable pair that exists. So we go through the actual algorithm. Firstly, each man will list the women in order of preferences from the best to the worst. So you can see this is the men's preference list for each guy. And then each woman will list the men in order of preferences. So you've got a man's list and a woman's list, and they've each ordered them. At the start of it, everyone begins unengaged. So at the start, there'll be no matches. And then while they are unengaged men, each man proposes to a woman until the woman accepts. And then if an unengaged woman accepts, she'll accept the first proposal that she gets. If an engaged woman receives a proposal that she likes better, she'll break off the old engagement and accept the new proposal according to her rankings as she goes through it. So might seem a bit confusing, but if we go through example quickly, so you've got these two lists. You start at the top of the man's one. Raimo proposes to Anne. Anne's not matched, so they make a matching. Saiku then proposes to Inka. Inka's not matched, so they make a matching. Tamo then proposes to Anne, but remember Anne was already matched to Raimo, but Tamo is higher up on Anne's list than Raimo. So she leaves Raimo and accepts Tamo. And you basically just carry on like this until everyone gets into a match. And if you follow that procedure, everyone gets into a match and all the matches are stable. So you may have noticed that the pairing output by the men proposing algorithm is male optimal. And if it's male optimal, then it's female pessimal. So if you look at some other examples, so this is also matching. It's a perfect matching because everyone has one pair, but it's unstable because Anne and Tamo like each other better than their current matches. This is also a perfect matching, and if you look at it, it's a male optimal match because the male got to select first. This is also a perfect stable matching, but it's a female optimal match because the females got to pick first. And you can see on this one, Eva and Anne are better off than their previous one. So there are different combinations that exist depending on which side you start off with. So you can see the Gale-Shapley algorithm involves a number of rounds or iterations, and this process is repeated until everyone does have a match. And in terms of algorithm coding, that would be what we go through. So you do it until the end, yeah. And then just some variations on it. So that what we went through was the basic form of it, but obviously as we're adapting it to all our situations, it doesn't really fit exactly. So Gale-Shapley developed this algorithm, and through the years, it's been researched and developed into various other forms and uses. So obviously it doesn't seem right that you either have a male optimal matching or a female optimal matching. So you do get optimal matching for both groups. It does require quite a lot of rotations and iterations. So sometimes it can get quite computationally intensive if you increase your set size. You get variations that involve uneven sets. So the basic form, you need equal number of men and women, but there are variations where you will end up with some people that do not have a match, which would be similar to our demand and supply. We won't always have equal sets. You get the one-to-many matching, which is the hospital resident problem. So you've got one person and the hospital can take 3 or 4 matches. So that's just a basic outline of that one. And then you got the stable roommate problem, where it's not a bipartite graph exactly. It's working off the same set, and you almost create this matrix form and work through a variation of the problem from that. So what I've been working on is trying to adapt the stable marriage problem for our supply and demand company. So you've obviously, at the first, we've got one product that we're trying to get from all your supply companies to your demand companies, and there's a whole, so the problem comes in is how you create that preference list. So there's a whole different ways you can look at transportation, you can look at distance from each other, specific costs. So as a start, you can rank these two according to your highest companies, however many units they have. So you rank it from your highest to your lowest, and you start matching from the top. Or you can create matches where you create the identical matches first. So example, the 1 and the 1s and the 2s and the 2s. And that sort of prevents you from having to break up units in companies. And that would be a cost saving later on as well. So there's a few of those that I'm currently exploring. And obviously, looking at them, you'll have different outputs from them. So you may have a lot of different matches. So number of matches may be one metric that you look at in the end. And then obviously you want to minimize the unmatched amount at the end. So if you can create all your matchings with no unmatched amount, that would be great. So that is something else that you would also look at. So for future work, or work that I'm currently on, but for future seminar series, I'd like to explore some of the other algorithms and dive a little bit deeper into that. So the simplex and the transportation problem, which follows quite nicely from the stable marriage one, and then the Ford-Fulkerson one. The big O notation, which has become quite handy in understanding as well. So that I think will be a good seminar series. So it's really looking at the computational efficiencies of these algorithms. So some of these algorithms, and you've got different variations of your stable marriage problem, some may look more efficient than others, and some may look like they create better matches than others. But maybe because they've got 3-4 loops in each other, as your set grows, your computational efficiency becomes a lot worse, and our small little computers may not be able to handle it. So that's something to look at as well. And then to look at in the future, once we've got these bank of algorithms, then I'll run a case study on all of them and look at all the metrics to almost do an efficiency testing as to which one is better than the others. And then we can compare the outputs. And then just before we end as well, so I just want to bring it back to our industrial symbiosis problem. So we all know why we need to create these matches between supplies and demand companies and create this network. But I think it's important to also bring this concept back home to us. So we live in this world at the moment where everything's quite a wasteful environment. And I think in our own personal lives, we can create a small industrial symbiosis network in our own homes, for example, maybe recycle more, reuse more. But it really comes down to one man's trash is another man's treasure, and using that in the most effective way that we can. Yeah, thank you. Any questions?
Okay, thanks, Delincia. That was a very well presented presentation. I think it was well explained, especially in the context of industrial symbiosis. And I like that you also gave a bit of a primer in graph theory, because it seems like that's the main, that's your graph representation that you are going to explore, these matchings. So well done. I think I'll open the floor to questions. So if there's anyone that has questions, I think from my side, with regards to the stable matching problem, like there is a bit of, I actually wanted to implement the stable marriage problem in my study, But the professor will know I immediately got scared, because when you mentioned the variations, like I know the stable marriage problem where you don't have equal sets of suppliers and consumers. There you have to implement local search methods, and it becomes very complicated. So I was just wondering how you're going to overcome those issues, and especially when you do have some ties with regards to who wants to match with. So a supplier may have two consumers they would want to match with. So how would you resolve ties in the context of stable marriage problems?
Yeah, so I think it does get quite complicated. And when you have all these variations, trying to create your preference list and then also wanting to create the most optimal matching, you end up with a lot more steps than the basic stable marriage problem. And as I said, that becomes a lot more computationally expensive or more complicated. So I've been trying to simplify it as much as possible. And I think in the beginning, I tried to, so you're looking at it you've got all these companies and they've got all these feed and waste streams. But as a start, for me to understand it a bit better, was to just use one product that's going from a list of suppliers and a list of demand companies and trying to match the one product first and then moving on to multiple products. So that was the one thing. And then the other thing with ties, so I think for me as a start now, you just have to make a decision as to whichever one wins on a basis of you choose a basis. So you could use maybe distance, one that's closer, because they're all giving the same product. Or one that I found was a bit better was to match all your identical matches first, so that you don't break sets. So that also works a bit better. Yeah, I'm not sure if that answers your question.
No, it does. Yeah, good stuff. I was wondering if there's any questions from the other members. Opening the floor. Okay, Palani.
Yeah, thank you so much, Sudan. Thank you, Delincia, for the very informative presentation. It was very clear, very concise. Just some questions. So I know you specified that it's an ON squared problem. And yeah, that is actually can become an issue when it comes to scalability. Basically, the more there's like that. Okay, yeah, that I want to say exponential, but that increase, the more candidates there are, then the computation time is going to drastically increase. Are there any ways that you've seen where maybe this can be improved? Or is it just?
Yeah, so from my research of looking, the basic form of the stable marriage problem seems to be, the ON squared seems to be the best, because when you go to all the variations, you're adding a lot more complexity and then it becomes even worse. I think ways in which we can improve it is by simplifying it a lot more. So I haven't calculated what it would be for my variations of the algorithm as well, but almost use that as a benchmark for the basic problem and then compare it to that. Yeah.
Okay. All right. No, that's good, because that's good, because I also had an issue in my master's where I had an ON squared problem. And one of the ways I was able to to make it better was I think using appropriate data structures. So there's a very nice book. It's called Introduction to Algorithms by Thomas Coleman. There are some nice, it's how you structure because I know you're working with these bipartite, this graph. So
yes,
apparently, but I don't know how applicable it would be for your case. But maybe even, by the way you structure your data and how you structure the relations, I mean, is one way that you could improve significantly, can have improvements on computation time. So yeah, I just wanted to, suggest that as something that you could do. So there's like, there are priority queues, there's stacks and so forth. And yeah, if you want to chat about these, Yeah, I am available. We can chat.
I'll definitely
anytime.
reach out. Yeah.
Yeah. Yeah, because I've worked a bit with kind of this. They really can improve. Because in my case, I think there was when I started off, it was it was taking 2 weeks to do a computation,
Sure.
and then it came to a point where when I kept finding these, and it dropped to like 3 minutes or so. So
Sure.
they can have significant impact in that.
Yeah, that would be great, and to not get stuck in that few weeks loop. Thanks.
Yeah. Okay.
Yeah, Professor, I don't know whether you put your hands up or you agreed with Plani.
Yeah, that was a hand up because as a host, I don't have a hand up option, but so I do have a question, but I think Zamishka's hand up was up first.
Zamishka, to you.
Yeah, Delincia, from listening to your presentation now and thinking about the stuff that I was working on, it's fairly simple, as I'm sure you would have seen. Not simple, sorry, similar to my not simple, sorry. So what I wanted to ask was, so you mentioned that you had your list of suppliers and your list of the dependents or demands, really, the companies. So is that what you're feeding in first? So you already know who's the suppliers and who's the demand? Is that what you want?
Well, yeah, I haven't used real case scenarios. So now I've sort of used made up scenarios. So a list of companies and a list of demands, and been playing around with the amounts on each to see how the algorithms work. So creating almost perfect matchings with the few companies. And then as you add on more companies, sometimes the algorithms just break. So just been testing it out myself and manually inputting it and changing it. And you would get a list of companies with their chemical constituents and feed and waste streams, and that would be your input. Yeah.
Okay, because I was just wondering how they tied in together, and I realized from my output, I already grouped the companies, but I'm not doing it by supplier and demand. So then I feel like I'm not sure, but yours sort of comes after that when you know who's the supplier and who's demanding, and then it works.
Yes, yeah.
Going forward from there.
Yeah, so yeah, I think that works, yeah.
Thank you.
Yeah.
Professor?
Thanks, Sid. So maybe first on that question, yes, those are different problems. Your study, Zamishka, is in how do you identify members of groups, whereas Delincia's is if you have groups identified, what are the best ways to then match them? So, in fact, one of there are two comments I have here. One is on Phil's comment about the order and the n squared issue. And I had been thinking there might be a way to create subgroups. So if you have, let's say, 50 companies to match, and then if you broke that up into two groups of 25 companies each that needed to be matched, it's still an n squared order, right? But as you form smaller subgroups, even though it's n squared, the saving in computational time is not linear. It's actually exponential as you create more subgroups. So you could look at grouping things on some of the critical parameters that influence industrial symbiosis, things like location. So of course, geolocation is an important factor in the matching. So you could have a kind of pre-processing step where you take all your companies and you create groups based on, it's largely the general guiding principle is on the cost of the match, and geolocation is one such factor. So that's one thing that could be done. And then,
Thanks for that, Prof.
Right. And the other question I had was, and I don't know if you plan to cover it in a future. You've clearly thought about a series here, and you've scoped each presentation quite nicely. So I'm not sure if you plan to cover it in a future one, but of course your stable marriage problem is for, in effect, quanta. So you've got a quantum, one woman is a quantum and one man is a quantum. Now, if you are doing matches of companies like that, you are limiting, you are in a way adding a constraint to your matching, which is that a company could sell a portion of their byproduct instead of selling the whole thing as one quantum. So and there are options we had discussed around that. I was wondering whether you had planned to cover that in a future one, or is it something you'd like to comment on?
Yeah, I haven't planned to cover it, but yeah, I'll certainly add it in. But I think one of the things we discussed is breaking. So a company only wants to maybe move a certain portion of their product to a demand company. So you could break that company's portion into smaller portions so that it creates one match. So maybe have a unit, so maybe 3 company A's with each a unit, and then you can create the matches based on 1 unit. So that might also increase your N number as such, but that is one way of combating it, I think, and I'll think about that further for a future series as well.
So I think it's an important one to work out, because you see that's the fundamental difference between the stable marriage problem and the industrial symbiosis problem. In IS, we are free to change the quantity. In stable marriage, it's necessarily between the quanta. So and there are different options you can think about. You could simply partition all available quantities into individual units, the lowest possible quantity, or you could have the company specify what that minimum is. So it might be that it's still feasible to sell something at, for example, 10 kilograms, or it could be that the preference could be used to. So, for example, a company prefers to sell more of its byproduct in a larger batch. So with some creative modeling around the preferencing, you could address this issue of quantizing the amounts involved there. Okay,
yeah. Thanks for that. I'll give it a bit more thought, on how we're going to combat that.
Okay, thanks, Professor. Are there any more questions? Zidane?
Thanks, Sid, for handing me over. I think, Delincia, even the book that Palani suggested, Prof and Sid pointed me to that book a long time ago, I think in April, when I was also looking at algorithms. But in particular, one of the problems that I encountered was working with the percolation problem, where you want to find the optimum way to get from point A to point B, where these points are opposing faces of a plane, so to speak. And runtime complexity, which you spoke of, is a significant thing. But I think one of the methods, like just adding on to what Phil said, of trying to make it a bit faster, is even if you detail your priority. So even if you detail, like Prof spoke about geolocation and distance, but even if you say, okay, you know what, we want to prioritize mass of the particular chemical we're matching, or the physical state, or the form, the yield, purity, things like that. It may be possible to kind of reduce runtime, specifying things a bit better. But then again, it also comes into how much of complexity and specification do you want to put in, and how much is it really going to yield? I haven't looked at it, so I'm not too clued up with that. But I know I have dealt with a problem like that before. So,
yes, yeah. Thanks for that. So you could almost use those specifications as your preference rating, and maybe get a collective preference rating based on all the specifications as well. Yeah, that's an option.
Okay, thanks, Zidane. So I think everyone knows that with these seminars, it's usually split with the technical questions and then any comments or questions with regards to the presentation itself. So I'd like to ask if anyone has any comments on the presentation. Zamishka?
Yeah, I really like that example you worked through with the people. I feel like that really helped us understand the stable marriage problem very simply, because when you mentioned it before, we didn't, like, I don't speak for everybody else, but I know I didn't really understand what it was. But when you went through it with a simple example, it really explained all the concepts really easily, and I think I understood it really well. So that's just my point on your presentation.
Yeah, thanks for that. I think it also helped me because I started looking at the simplex problem and all of those are quite mathematically complicated and intensive. So when you look at this in a simple form and you see its applications, in the medical residency, it makes it a lot more appropriate. Yeah. Thanks.
Professor Rautal? Sorry, sir, you're on mute.
Yeah, thanks. Okay. So, in fact, I don't have any criticisms. It was, I echo the sentiments by many here, which is that it really was a very good presentation. I really liked how it was quite clearly contextualized from the beginning. So it was very clear what general problem you were working on. And also in terms of showing that example. And it's a comment that I've made to several people before, that when presenting on algorithms, it's not enough to hand wave your way through it and assume that something is known. And in fact, in our algorithms, quite often there is there will be a specific point in that algorithm. There's a specific step which is relatively easy to understand. And of course, it has fantastic outcomes. The implications will be that you can solve very complicated problems, but it's often a very simple step, which is not difficult to explain. And if you've taken some time, as you've done, to explain that step, people really feel that they've learned something new there. So it's something I would really encourage everyone to look at doing. And yeah, in fact, if you could share your presentation as a kind of template or a way to present, I'd appreciate it.
Yeah, sure. I'll put it on the seminar Dropbox folder.
Thanks.
Are there any more questions? Okay, so it seems like we have some more time, but I was wondering. And usually it's at this stage where we hand over to the host, Professor Rautal. But if I could maybe just comment, because there is a bit of work, there is a bit of similarity between the work Delincia is doing and myself. In terms of I just want to, I think maybe give some advice with these transportation problem. I found that that's the best way to incorporate the simplex method, because it gives you a structure in which you can automate the process. So when you are creating your sets of data where you have M number of suppliers and N number of consumers, the simplex table itself, there's a set routine there that can be automated, and you can get your results from it. And you did speak about metrics, and that's one of the things that I'm using to compare my algorithm. So graph metrics, I think, you did mention it. So just have a look at graph metrics and see how you can extract them from your results. So without further ado, I think maybe I'll hand over to Professor Rautal.
Thanks very much, Siddhant. It's a good comment. In fact, it might be useful to have one whole session on that topic, because the approach that we are taking in your study, Sid, is also one that we are taking with the Delincia. So we are also generating multiple graphs and multiple scenarios with, through randomization and some kind of controlled specifications. And then to see how the algorithm performs on multiple such graphs, and then and to test that performance through the graph metrics. So in fact, you might be interested in presenting on that topic, Sid, or yourself, Delincia, or maybe you could both collaborate and do a session on that topic.
Yeah, sounds interesting.
That'll be good.
Okay. Well, you can go ahead and close for us, Sid.
So thanks everyone for attending the seminar. I think the series of seminars that are involving industrial symbiosis has, given us more and more information. And I think Delincia has really broadened our understanding and given us a conceptual understanding of how industrial symbiosis can help South Africa on our way to becoming more resource efficient and hopefully one day have a circular economy. So thanks everyone. And take care. Professor?
Okay, thanks everyone. And maybe credit to all of us for not making the obvious stable marriage joke with Delincia's recent marriage. So, yeah.
Thank you.
Thanks everyone. Okay, bye.
Okay, bye.